Welcome everyone for the last lecture of ISSS course Introduction to Astronomy and Astrophysics. In the last 17 lectures, we had covered 5 modules. Our first module was just an introduction part. We learned how the astronomy evolved from the ancient era to the modern days. In the second lecture, we had covered our neighbor planets and also learned about their moons. Then we learned how distance are measured in astronomy, and we got familiar with the idea of the coordinate system. For the second module, we had introduced sun, solar cycle, the solar phenomena, and also the second module covered about the evolution of stars. We learnt about different types of stars according to their mass, temperature, their spectra. And the last lecture of the module 2 was about the exoplanets, how to determine or the presence of exoplanet, what are the techniques for detection of exoplanet, we learnt in that lecture. For the module 3, we had covered 4 lectures of galaxies. We learned about the different kind of galaxies, starburst galaxy, active galactic nuclei, quasar, all those sort of special kind of galaxy, and also the different types of normal galaxy, that are the spiral galaxy, elliptical galaxy, irregular kind of galaxy. And the main thing we introduced in our third module is the use of the NED, the extragalactic archive database, which have information of the coordinates of those galaxies, the surveys those covered those galaxies or discovered those galaxy, or those surveys which has studied those galaxy has been covered in the lecture, in some of these lectures. And we learned how to download or how to check if a galaxy is covered in some survey. And also we checked how to download, how to get the information of different properties of galaxies from the NED website. For the fourth module, we learned about we recap our basic physics lessons with some high school physics or some UG level physics, and then we were introduced to the tools of astronomy, different kinds of telescopes. In the fifth module, we covered the history of universe, how the universe started at Big Bang, how it got evolved, how the structure formed, and what were the different main eras in the history of universe. In our last module, we are working with Python, or you can say we are working with the use of Python for astronomy. And in this module, we have already introduced Python to you, and then we the first lecture itself covered the Python basics. The second lecture, which was the lecture 17, the yesterday or the day before we uploaded this lecture, this covered the astropy quantities, use of astropy quantities to learn for doing the calculation using astropy, the Python package specifically for astronomical calculation. And then we learnt about the model fitting some kind of model, some models that may be linear model, non-linear model, using the astropy and the scipy, these two packages. And also we learned how to query some data set in using the Vizier from the Vizier database, if you have the Vizier ID of that dataset. And then we had already learned about the use of matplotlib and the seaborn, two plotting library one thing to mention, the seaborne makes some more steady kind of plot, and the seaborne is specifically for dealing with the statistical dealing with dataset in the statistical sense, and with very few one line or two line you can plot different kind of statistical results from your dataset using the seaborne. In this lecture, this final lecture, we will cover how to download image cutouts from the HIPS to FITS, this website we already mentioned, and then we will plot some of the images using the Astropy and the Matplotlib. Next, we will cover the observational planning part, that is finding if any particular source is observable tonight from your location. If you specify your location longitude and latitude with value in the Astroplan package, and just run few lines of code. Then today's lecture, if the time permits, I will introduce how to use AstroQuery and write some standard query language in AstroQuery, and access the SDSS dataset using the Python. And then in the final part of the today's lecture, or in this course, we will plot the spectra of different SDSS galaxies, or I will show you how to plot the spectra of SDSS galaxy if you have the specific ID for the SDSS galaxies. So today we should go 1, 2, 3, 4, 5. In this lecture there are 5 notebooks will be covered today. So here, this is our spreadsheet, you can just go to here, ISSS course notebook, and you will see that I have uploaded the different notebooks here. The notebooks, those were covered, or for those are necessary for today's class. So the first thing I will do, first thing is image download. This notebook I will run. You all know that the position of any extragalactic object is defined with the array tick in the celestial sphere, and you know, in the use of NED for observing for the checking the array dick of some extragalactic object. Suppose you just go to NED. So first I should go here, the HIPS to cutout browser. Let's go to Google, then HIPS to cutout. Just bookmark. This is the web page from where I will download the FITS cutout from the different surveys. So in astronomy FITS image, you often encounter this term, that is in astronomy, FITS, or the flexible image transport system, is a standard file format that is used for storing images or data tables and other related information for the scientific computing. It is widely used for storing images or spectra from the telescopes, and also the data, and they store metadata such as time, when which telescope took the data, what instrument used the which instrument was used during the observation, what is the coordinate system of this observation or of the object observed, and who is the PI of the project. Those all the things are stored in this FITS metadata. So FITS has two type of thing, one is the metadata and another is data. Some key feature of FITs include that FITs have the header that is known as HDU. FITs files are organized into different HDUs, each containing is consisting of header and the associated data. The header contains the key value pairs describing the data, such as when the observation was done, which instruments was used, what direction the telescope was pointed for the observation. And this FITs has the data flexibility. FITs files can store various types of data such as the 2D images like the photographs of the sky, 1D spectra like the light curve, or the tabular data such as measurement from the multiple observations. Standard format, FITs has been around for the decades in here and is supported by many astronomy software packages. This standardization allows researchers to share and analyze data across different instruments, different telescopes and software environments. FITs files can support lossless compression, which reduces their size without losing any data, making it easier to store the large dataset with FITs. And there are many astronomy software which can load FITs data, in which you can load FITs data, you can view FITs data. Some of those software are DS9 FITs liberated, and also using if you have the Python coding, then you can access the FITs file with the Astropy package, which we will do in this course. Now for downloading the FITs file or the FITs image cutouts of arbitrary size and resolution, we will use this web page, that is the web page, the HIPS to FITs service. So now I will first do the thing. Suppose I want my target is NGC 1300, a bird galaxy. Now I want to plot have the Panster's R-band view, optical view of this galaxy. Now so the first thing, I have to give the name of the target here, NGC 1300. I want to give the dimension. Suppose I want to have the square grid image, then we can just give the equal pixels and x direction and y direction. I have selected the survey, selected the target already. I have selected that projection. Image size, suppose I am giving image size of 0.1 degree, that is 60 arc minute is equals to 1 degree. So 0.1 degree is equals to 6 arc minute field of view. It will give me cutout from Panster's Tier 1 survey. Rotation angle none. So first I will view how this galaxy look. We know this is a bud kind of galaxy. Now I will download the FITs file. I should give this image size 0.2 degree, that is 12 arc minute. This is the galaxy itself. First I should download the FITs. We advise our participants to run this code if possible in your own machine, or if you are familiar with Colab, you can run this codes there. So this has been downloaded. Yes. Now in this ISSS course notebooks, this folder link has been shared to you. So I will first go to this image download. And if you go here, you can see here the main thing. This is the coding lines, just like your Jupyter notebook machine. And here you can check which data you have. I have just downloaded one data set. Download. This is 544 Renin. This image is Panster's Tier 1, NGC 1300 bar. Now I will transform this here, desktop, so that it is easy. The file which you want to work with in this collab directory, you have to transform this here. So in the desktop, just go to the pansters fits. Ensure your files are saved elsewhere. This runtime files will be deleted when runtime is terminated. Okay. So the file has been downloaded. So first check what is the directory. If your file is there, pansters dir1 ngc1300 bud.fits. This file is here. Now the main thing you have to do, this is a Galaxy NGC 1300. I have downloaded the pansters DR1 R-band image. Now for plotting, first for initiating any notebook, first write what the packages you want to use here. So NumPy will be of course used. The matplotlib will be used for plotting. Matplotlib inline, plot within the notebook window. You have to import write this from the astropy.io import fits. This will help you to load the fits in your notebook, and this astropy.wcs will help you to plot the coordinate system from the file. First you just load it. Import NumPy as np, import run it matplotlib.pyplot as plt, matplotlib inline. From astropy.io import fits, astropy.wcs import wcs. Now you have to mention that the image panster is equals to, you have to give the file name, and you have to write it, pansters dr1. I should copy it from here. Pansters given ngc.fits. This is the image panster. This is opening. You have to access for accessing the image. Yes, I should just say. Okay. Sorry, the name. Here I have to give impan. This is the astropy.io fits.hdu image, primary HDU. So now I have to just add impan dot HDU list. Impan 0 dot HDU. Impan 0 dot HDU. Sorry, impan 0 dot data. So this is the data set. I have to find HDU list astropy. So if you just write here image.download impan.info impan.info impan.info. So if you just write the impan.info, then it will show you what number of HDUs are available. So it is showing here that only one HDU is available. Each HDU contains header and data. In some of the file there can be 3 HDU available or 4 HDU available. So these are some subslot. You can say this is some subslot. If it is advised that if you cannot just memorize or get anything, you are very free to check with the documentation itself. Maybe for in many cases we cannot, we people just forget what was in the documentation, because sometimes we run the other's notebook, sometime that happens. Now impan, you have to just get the thing. Impan, you are just getting the HDU file, what number of HDUs are available. So one HDU is available, so you have to access that HDU file. I have to delete this first. This is impan.info. Impan 0 is the first HDU, and in the first HDU there are two things, one is the data and another is the header. You can just check what is in the first HDU. Impan 0. Impan 0 has two things. It contains data and a header. And this gives you number of HDU in the file, number of HDU list in the file. Impan0.info, impan0.data. This is your data set, the full image array, and you can access the header. So it is giving the different information, that at the pixel coordinate of reference point, x-axis and y-axis, the geomonic projection, the CR val 1, CR val 2, longitude pole, latitude pole, and the telescope information from where this data has been taken. Now this is the image, this is our image of NGC 1300, image 0 header. Now I should write image NGC 1300, comma, origin lower, plt.x label. This is pixel value. This I should first check what is this coming. NGC 1300. Yes. So here x-axis and y-axis are in pixel. You can see. I should just write plt.x label within the pixel. plt.y label. Y label. This is also in pixel. our task is to plot this in the array deck format. For that, for plotting array deck in a image cutout, you have to import the world coordinate system in the folder WCS. So for that you have to from astropy matplotlib.colors import lognom WCS astro. Well, the WCS is WCS astropy. Alright, WCS. So you have to import this line. This is within from astropy.wcs import WCS astropy.wcs import WCS. WCS panster is equals to image panster. Your image name is image ngc 1300. Image name, you have to give the header part only. In pan 0 dot header, you have to give the header part of the HDU. Image panster 0 dot header, HADER header. So the image in which you want to label array deck coordinate, locate the HDU of that image and locate the HDU of that image and give the header of that particular HDU to WCS. You can view this thing. What is the header? What is the HDU? Or you can just write print WCS span. The next part we will just plot the image with this WCS. Now you have to just add this line. Here you had the thing. Just add one line, that plt.subplot projection WCS span, and the show will be same. Here you can see that your image has been plotted. Here X label and Y labels are not the thing. Array and deck. So this was our introduction to the plotting the array deck coordinate with AstroPy. So for plotting any kind of cutout that is downloaded from the Hips2Fits browser, you have to first just load this in your working directory where you are running this notebook. Then you have to just import the fits and the WCS from the AstroPy. Then you just do few lines here and you will get the plot. So this ends this discussion of image plotting. Now for the second part of this today's lecture, we will do the observational planning, I guess. I should check that. this too has been done. We have to now do some observational planning. So for observational preparation, so this is the notebook. Sometimes when you will run this notebooks in the machine, you will get that this some packages are not installed. I will tell you that just do suppose it is showing that Astroplan is not installed, then you can just write the pip install Astroplan, then you rerun the code just like this. You will get the code and rerun. If you rerun, then it will be installed. So first you can see cannot import nem get moon from astropy.coordinates. Get moon, get sun, get body. Just it is not running. Just uncomment this code for now itself. Astropy.coordinates. So for astro planning, this tutorial has been taken from the growth school example, and also some of the inputs has been added. So for this tutorial, there are few packages extra needed, that are Astroplan and the PyTZ. If they are not installed in your machine or the collab directory, I will suggest you to install that with those with pip. And first thing, you have to import the numpy. You have to import the astropy import units as you. Astropy.time import from the astropy.time import time. From astropy.coordinate import the sky coordinate. From astropy.coordinates import the earth location. You can just check this. Import PyTZ, then matplotlib inline. From Astroplan import observer and the fixed target. That is the fixed target for the celestial sphere. And from Astroplan utilities import conf, configure those, and there is some few import from the Astroplan. This code now, we had already installed Astroplan in my workspace. If you can just write the date, this is 4th April. Now you can plot which time this code or the this collab notebook is running. Now if you just write time.now, you can write in the MJD format, JD format, decimal year format, and then you can see what is the time now. This is 4/4/2025, 12 hours 34 minutes 20 seconds. It gives the time in the coordinate standard time. Coordinate standard time, standard D standard time, or the UTC time, or the Greenwich time. So this is 5 hours 30 minutes before. So if you just add the 5 hours 30 minutes, it should be 18, yes. So this code is now. Suppose you want to know what will be the time after 3 hours in the UTC format from now. So you can add the 3 hours 30 minutes just like this. Print in 3 hours 30 minutes, the time will be now plus 3 hours plus 30 minutes. This will be 16:05:10. That is about 16 plus 5 plus 30, that is 21, yes, 9 hour 9:30, around 9:30 p.m. So using to keep the accurate time, the changes in Earth's rotation periods have been taken account. Astropy does this by convention called the UT1, that is tied to the rotation of Earth with respect to the position of the distant quasar. There are one system, that is the International Earth Rotation Reference System Service, which keeps the continuous tabs on the orientation of Earth and updates the data in the ISSS bulletin. There is something, and you can check UT1 minus UTC difference, which is very small, but taken care with Astropy. Now we will see which observation sites are available in the Astropy. So for that, which observation sites are available with Astropy, with Astroplan, Astroplan or Astropy. With Astroplan, Astropy, I should check. So you can just plot the sites names. You have to write the Earth location dot get sites name. You will get that many observatories are available here, or you can print this. This is not visible here, and print. You can see some of the Indian observatories are available also. Here is the thing, DAO. I will show you that some Indian observatories are available. One is the HCT, one is with I. There is one observatory GMRT available, Giant Microwave Radio Telescope, available with two names, Halley Telescope, Happy Jack, HI, Indian Astronomical Observatory, that is the observatory at Hanley, or the position at Hanley is available with Astropy, you can say. And another observatory is Vainu Bapu Observatory, that is also available here. I should just go there by skipping. You can check which observatory, different observatories location, how changes. Vainu Bapu Observatory is also available. I should just check for later. We should check. This is one of the question for you. Plot position of observatory of Indian observatory, of Asian observatories. Position of few observatories. There is on longitude latitude plot of Earth. Latitude plot of Earth. Now you will see, you have seen that the Indian Astronomical Observatory or the Hanley Chandra Telescope Observatory is available, but you can put the observatory's name with the two names. One is you can just mention what is the longitude, latitude, and longitude, latitude, and elevation. This three term, and just here, or you can mention that with the name. Suppose the longitude of the latitude, elevation I know from the Google, and I have given that, and the location, for setting location you have to write the at location from geodetic, longitude, latitude, and elevation. Then you have to fix an observer at that observation site and create the observation, create the observer. So location is equals to location, time zone, and you have to specify one name and some description of the telescope. This is the Indian Astronomical Observatory, Hanley. Another way you can load observatories, on Earth just by name. Load observatories on Earth just by name. You have one observatory, Subaru, in this list. So I have just plotted observer at site, Subaru. So this is creating an observer. This is created as observer. So you can say what is the longitude, and the elevation of that observation site. Also, I have been choosing another observatory, ISSS site, that is longitude, latitude, elevation has been given. Also for the Vainu Bapu observatory, there is the keyword is available in the list. You can find it. So here also you will plot, you will get the details of the location, VPO. VPO. Also another observatory is the Devasla observatory, that is that location I have also given here, location and the longitude, latitude, and the elevation format. So I have given the name here, longitude, latitude, elevation. Location is the Earth location, geodetic, longitude, latitude, elevation. Here there are two telescopes, LMT telescope and the Devasla optical telescope. One is the liquid mirror telescope and another is the optical telescope. So here also I have created a position an observer in the DOT. Here you can just print 79 degree 41 minute. Let's get it done. 30 minute means 0.5 degree. So here would be 0.68 is okay. 29 degree 21 minute. 30 minute, less than 30 minute, that's this, less than 0.5. You can just print. Now we will calculate how long there will be night at Devastal. So for making this night thing, we should introduce one concept of the toe light, that is the period of the time before sunset and the after sunset, when the sun is below the horizon but still illuminates the sky. So for the night observation you have to be within this civil toe light. So here is sunset. When there is less than 6 degree, that we call the civil toe light. Less than 12 degree, we call the sun is 12 degree below horizon. This is the nautical toe light. And when the sun is 18 degree, this below horizon, then we call the astronomical toe light. For today's observation planning, suppose we will be dealing with the astronomical toe light. So for that, suppose the sunset, when I want to know when will be the sunset at the Devastal today, and what will be the evening twilight, what will be the midnight time, and what will be the morning twilight, and when will the sun rise tomorrow. So for that you have to just give the observation position dot sunset time, twilight dot evening astronomical, dot midnight dot morning astronomical, dot twilight morning astronomical, and dot sun rise time, and we should print those. So you can see just at 5 hours 30 minutes after that. So 5 hours 30 minutes, that means sunset at Devastal will be 5 hours 30 minutes. This is about 13 18:30. About 18:30 today there will be sunset. The twilight will be start from 14:22 that is UTC, that is at 5 hours 30 minutes. So 5 hours means 19. Around 7:30 the astronomical twilight will start, and the midnight will be this plus 5 hours 30 minutes. Astronomical morning twilight will be at 23 plus 5, that is 24 plus 4, around 4:30 there will be 4:30 or 4:35 there will be astronomical twilight, and the sunrise will be around 6 from Devastal. Now we can calculate what will be this values if we just calculate get this is the thing, calculate sunrise time for Devastal. Now we will plot the or find the same thing for the Hanley Observatory. So we have to just specify the IOA Hanley, and then the other things would be same for Hanley. You can see there is some small variation here. Now you can find how what will be the observation time, and here you have to do but just minus the thing, morning twilight minus evening twilight plus evening twilight, the thing when the observation can be done, and you can convert that to hour using unit of Astropy. You know we had introduced that concept. So at IAO there will be 8.5 hour around 8.5 hour, the duration of the night will be 8.5 hour, and for Nainital or the Devastal Observatory the duration of night is about 8.7 hours. Duration of night calculation, duration of night, taking care of astronomical twilight, taking care of astronomical twilight. In astronomy you will often find one term, that is the local standard time or LST. It is a timekeeping system that astronomers use to track the position of the celestial objects on the sky based on Earth's rotation relevant to the stars. Available LST in a particular observation site is the range of local sidereal times that are available during observation, and from using the local standard time during which the with this time the observations can be made at particular observation site. So this local sidereal time and there are two concepts, local sidereal time and the sidereal time. Sidereal time will be introduced first to you. Sidereal time is the timekeeping system which is based on the Earth's rotation relative to the distant stars, not the sun. The sidereal day is about 23 hours 56 minutes, and 4 seconds, which is slightly shorter than solar day. Local sidereal time is the sidereal time at particular location of Earth, and it varies depending on the observer's longitude. It tells that the position of the stars at the given moment at the night sky. How LST's concept is used during observation. Position of celestial objects. The position of star or the other celestial object in the sky are primarily determined by the observer's LST. This is because the celestial objects rise and set based on the Earth's rotation relative to stars. Astronomical observatories use LST to schedule observation of the specific objects. Each object in the sky is visible at a certain LST depending on the right ascension of the coordinate. The LST at the observatory help to determine when the object will cross the local meridian, or that is the thing when the highest point of the sky the object will rise. What is meant by the available LST concept at observation site? Available LST refers to the range of local sidereal time during which the observations can be met for the maximum elevation of the object. This range is determined by the observable objects. Each object has a particular right ascension that corresponds to a specific LST. When it crosses the observer's local meridian, the point that is directly overhead, the site's equipment capability, available LST can be restricted by the time of year. During certain seasons, some object may not be visible due to Earth's orientation, and the observatory's ability to track different parts of the sky also affects the site's equipment's available LST. And the time constraint. Practical constraints such as the amount of time for the observation may define the available LST window, with the observatory only being able to observe the object within a certain LST range during the given session. Suppose in an observatory is trying to observe a star which is at the array of 10 hours. Then the LST time would be needed around 10 hours for the stars to be crossing the local meridian. Therefore, the available LST, I have to just check. Therefore, the available, there is a typo. Therefore, the available LST for observing the stars will be range around this value, depending on how long the stars or object is visible and the observational capabilities of the site. In short, by available LST is the period during which the object of interest is visible on the sky near the local meridian, and it is accessible for observation for the particular site based on the current LST time at the location. So now you can check what is the LST, what will be the object's LST today at now, and what will be the object's LST at midnight at the position Hanley and at the position Devastal Optical Telescope. So LST now at Hanley and LST midnight at Hanley would be this LST now Hanley, LST now Hanley, early Hanley, LST at IAO, Hanley midnight Hanley. So LST at IAO now is 6.272 hour, and LST at IAO in, when the today's midnight will be 12-hour angle. So it is better to observe the 12-hour angle, the sources which are near 12-hour angle, that is the source with the array 10 hour 20 hour 10 hour to 14 hour, around those hour angle LST. Now you can find the what source. If you want to observe any source at from this Devastal site, which sources you can consider, or which array range you should consider. That is the LST now at Devastal. Now LST now Devastal. This is the same around 12 or 13 hour source. Now we can do another thing. This is the thing for your to do from your end. How long will the night today? How long will be tonight? How long will be the night from the Cake Observatory site? From the Cake Observatory site. From Cake Observatory site. Will the night? Okay, is that tonight? Which object? Which? Is better. What LST is available? What LST is available at the midnight at Cake Observatory site. Cake Observatory site. Now in the Astro query there are two things. One is the body and the target. Body refers to the astronomical objects that are the comets, asteroid, planet, that are the solar system, inside solar system object, so which move and has a changing position in the sky over the time. This body is a more dynamic way of handling their coordinate, and often they involves the time-based ephemerides, since they are not the stationary like the stars. And the fixed target in Astropy is the refers to the stationary objects on the coordinate celestial coordinate, and their fixed position or the array position does not change. And this coordinates can be specified as the fixed point in the celestial sphere. So this objects with the coordinate we fix the stars, and from the with the body objects in this astroplan we fix the objects like asteroids, comets. For planning the observation of the asteroids, comets, we will not discuss here. We will ask our readers to check how to do the observation planning for some specific comet or planet with astroplan. Now this course, this tutorial will give you a sense about how to plan observation for the stars or the galaxy. Suppose we will tell our participants to do some observational planning for a comet or asteroid with Python. Now for doing the fixed target observation, you have to first specify the comet. Suppose I want to observe the Andromeda galaxy M32. You have to give the coordinate name. One way you can just give this, you can specify the coordinates with hour, minute, second and degree, minute, second format, and just write M32 is equals to fixed target, name M32, coordinates is equals to coordinates, and you can get the hour, minute tuple. Now you can check if your target is available from the site now. So that is the thing you have to check. If the target is up the sky now, target is up evening twilight time. If the target is up at evening twilight, if the target is up the sky midnight, today midnight or the midnight of this day, and suppose I want to check if the target is available during the morning twilight. So it is saying that the target of M32 is now available, but not available at the midnight, not up the sky midnight, but it will up the sky tomorrow morning. Now one thing I should check whether it is available now. This should go. Yeah. Yes, because the time we are recording, this is the time of the evening twilight. Same way you can check if it is available from the any other site. So something it is going up the sky, then it is setting, then it is rising within the morning of tomorrow, within tomorrow's morning. So what the case? So you have to plot the elevation of this target first. Then we have to plot the elevation of the target or the altitude of the target when the target is attaining greater than 0 degree, then going less than 0 degree, and then again up. You can find that within the altitude and the azimuth of the target you can find at any specific position. So for that altitude azimuth you have to write that altitude this site name dot altitude azimuth. What is the altitude azimuth of the target for the evening twilight? You can check. The altitude is 2 degree 87 minutes, and also you can find the thing. IO Hanley now. You can just write now. So altitude. Evening twilight. Evening. Evening. Evening twilight. Oh. At the evening twilight there will be altitude azimuth. Now so evening twilight, so from the 20 degree this will go to the 2 degree. Yes, the evening twilight will start at 7:30 I guess, not the now. Yes. At the morning twilight, what will be the altitude azimuth? This has been mentioned. At the midnight, you can see the source is below the horizon. Then, because the source is not observable, well, here you can say. Another thing you can find, that is when the source will rise tomorrow. That is the thing, just at 5 hours 30 minutes. So 5 hours 30 minutes means 5 hours 30 minutes. Next we will focus another target, that is the Messier 51 target. For fixing the target, you can for fixing any target, you can give either the coordinate of the target, you can mention those by writing the numerical values, or another way, you know the name of the target, that is a messier name, ngc name, then you can fix just give the name here within fixed target. So fixed target 2 dot coordinate, suppose I am fixed target fixing target 3 another coordinate. Also for fixing any target, you can either go by adding the name, the array deck manually, or you can just write the name. Now the next thing we will do, we will not do today about the observation of the solar system objects. We will leave the solar system objects. Sorry. Solar system observation planning, solar system observation, solar system objects. Observation planning has been left. Observation planning has been left for participants. Git body. I guess git body should. Here. I guess get body is from Astroplan. We can check if with Astropy, Astroplan git body is available. This scope is working. Maybe there was some issue with the update. Need to install some package extra if you want to get this JPL thing. Not working. Astropy.coordinates.get sun dot coordinates get sun. Astropy dot coordinates import get sun. Okay, this is working. Get moon. Coordinates import. Why the moon is not imported? I will tell the readers to fix this error by your own. Get sun is working. Get body is not working. But it was working in my own machine. Maybe there is some problem with the astropy.coordinates version, because in my machine the astropy is old version of astropy. In this window collab, the newer version of astropy has been installed. Maybe there's some dependency error or something. This discrepancy is why. Get body, yes, astropy.coordinates get body is working, yes. So get body moon midnight IO. This is working. What was the problem? Which body? What was your problem? I was. What was the problem? Get sun, get moon. Get moon is not working. Get body is working only. Get body is working. Get sun is working. So you have to specify moon by just moon. So there is small error. Now you can just write the get body moon. This will give you the information of moon at different time. You can get the information of moon at midnight. You can get information of moon at evening twilight. You can get the information of moon at the morning twilight tomorrow. Now you can just plot, just see the one thing, that this array deck and this array deck position is changing for the moon position, and also you can check that is happening for other objects too. Here you can check get body. Here is the get body. Here a different solar system bodies has been given: Mars, Jupiter, Saturn, Uranus, Neptune. Suppose I want to know about the Jupiter thing, how the Jupiter's location is changing. Get body, you have to write the get body. Just specify the name. Checking the thing. Now, so this is printing the array deck or the position of distance from what? You have to figure out what is this distance, is distance from what. This get body, I should check here. Done. Sky coordinate and distance, maybe this is the distance to moon. The next thing you can plot now at evening twilight at IAO, that is 7:30 PM today. Evening twilight IAO. So there is some small change you can see. This is 7, around 7. This is and midnight. I should midnight IU. MIDNIGST midnight IU. There is some small change you can see. Now you can plot how bright is the moon at the midnight today. This is around 0.46, and also you can find for the different position there is nothing very, the lunar illumination is same around. And next thing you can check the solar system bodies. We found that we can turn solar system objects into the pseudo fixed targets and plan the observation. This is done by just fixed target named Saturn, fixing the target with respect to fixing the target with respect to Saturn. Now you can check if the target is up the sky at the position and the target name. I have specified two targets, one is the target 2 and target 3. So the target 2 was M31 and the target 3 was NGC 1300. So whether this target 2 and target 3 are available in the night sky at midnight today from the Hanley site, you can check this by the site name dot target is up, time and the targets. And the target 3, that is NGC 1300, it's not available tonight at Hanley. But the target 2, which is M31, which is available at the Hanley site tonight. Now you can just go with the target. So the target 2 is available. Target 2 is available from Hanley site. Let's at midnight. Let's plot elevation of that target. Let's plot the elevation of target. Let's plot the elevation of the target. The field map of target. You can just go to this alt azimuth. You can find the air mass of the target. The air mass will be 1.03 around. Now you can plot the position of the target at the midnight with the astropy.plots, importing plot sky, plot air mass, plot sky 24 hour. How will be the target's position changes with the 24 hours from now. For plotting the position of target at midnight, you can use the plot sky. So here is your target at midnight around 90. So how in this night the target's position will change across the sky. In the terms of altitude azimuth, you can plot that. For plotting that kind of thing, you have to give the time start will be evening twilight and the time end will be morning twilight, and time of observation a fixed array you have to give, and you have to plot sky at the for the target at the observation site, and you have to specify the time stamps at which you want the position of the target on the sky. Now you can see this is the position of the M51 target on the sky. Now how the 24 within the 24 hours how the target will change. You can plot the plot sky 24 hour. That is the target will go below 30-degree altitude at this 2 times, and then above 30, this is the thing, 0 15, this is 15, this is 30, this is 45, 60, 75, this is 90. So around up the sky here, this is up the sky. Also you can plot the how will be the air mass changes this night. You can check that the air mass is going around 20, it is attaining maximum around 20 UTC, that is 20 plus 5, that is around 1:30 p.m. tonight. This is around 1:30 p.m. tonight. So you can check around 1:30 p.m. tonight the target. You can check the here around 20 to 30 p.m. Here the target will be here. Now I will show you how to plot the field image of the target in the Python. Now you can plot that using the plot finder image in Python. You have to import the Astro query. You can see here sometimes when we run notebooks in the Colab, we see that some packages is not installed. So for that, here it is showing that Astro query Skyview, this line there is error, and here for that I have to just go to let's pip install Astro query UERY. Install Astro query. This will install your package. Collecting packages PyPO and Astro query. Now this should run. From astroplan.plots import finders image and astroquery.skyview import skyview. So here you can specify what field, cutout field you want, and this what is the plot finder image target 2. That is the available target. Skyview get images got a unexpected type error by this type. Skyview, you can check by this why this error is coming. It's working here. Not working. We will fix the error later. Left for you. Now we can specify a list of target at the observation site and check if the target is up now, if the target is up at the later time, at some later time. So if you just write the name of the targets, it automatically gets the information of the array deck of the target just by this code. And you can see which targets, whether the targets are available now from the observation site, whether this target will be available or up the sky. When the target is up, that means it is above altitude 0 degree. So you can plot whether, so at the midnight the first target, that is Vega, will be available, Polaris will be available, Polaris is all available, and NGC 130 not available, M42 is not available, M55 is not available. The target is up means this is altitude 0 degree above, but all the observations is not done at the above 0 degree. Just at the horizon you cannot do observation. Now for that you have to the target should be above around 30-40 degree elevation. You can check here that if the target is up the 40 degree, if the target is up 40 degree. Now for the target in targets, if any of your target is up 40 degree horizon, and this target altitude latitude we just find out, and how the altitude latitude changes at some observation site, we just give that information also we mentioned. So there the x-axis is in the terms of UTC. You have to add the 5 hours 30 minutes with it. Also you can plot how will be the altitude changes with time for the list of target. So you have to specify the timestamps with the array, and then you have to give this target site dot altitude latitude into target's time this code, and you have to append that code. We have left it for the students. And also you can plot the sky position of different targets in a single image using Python. And here you can see the time observation times is given. Also you can plot air mass, all the air mass in the same image. Now another thing you can do, you can give some constraint in the astroplan, constraint of air mass, constraint of the elevation, constraint of the distance from moon, and you can check give that constraint as some list that you want the altitude of the target above 25 degree, less than 84 degree, air mass you do not want to go above 2. At the night constraint, that target will be observable only, target I will observe only on the night. And the mole separation, the target will be at 10 degree from the moon. And here you can go the time range when your target is available. Give some time range, some time range. And you can just give the list of target and check if your target is at all following your constraints. And also you can check if the targets are observable from your side, if the targets are always observable or ever observable. You can produce such list using Astroplan. We will leave this codes for the participants. And also the thing you can also check the reconnect. Oh no, why not I'm disconnected. Another thing you can check in which month your target is observable. I will not read this code because sometime this runtime disconnected. No, runtime not disconnected. Suppose you want to know whether any target is observable from the in which month the target is observable from your observation site. Suppose I am at some observation site, that is the Munition Whitefield array, and want to check whether the Barnard star is observable or which month this Barnard star is observable at from our observation site. And our constraint will be I will do the night observation. I will be the do the night observation. That is the I will observe within the astronomical twilight, or in the astronomical night. You can say that is when the sun is below 18 degree the horizon, and the air mass uh, constraint will be less than an air mass constraint. I will maximum go for 1.5, and we can just get just within the few 1 2 lines I can get information whether in which month the target is observable from this observation site. Suppose here you can see it gives the months 3 4 5 7 6 7 8 10. Suppose I want to check if my target is observable from the month observable, when star is observable for my observation site IAO. Oh, sorry. IAO I had defined now. IAO Hanley. Sorry. IAO Hanley. IAO Hanley. HNLE Hanley. It should work. So from the February onwards to October, this Barnard star is observable at night after the astronomical or within the astronomical twilight, at astronomical twilight with the air mass constraint 1.5. Now this is the thing. I should delete this. This is 1:30. 1 hour 30 minutes. So for the today's lecture we had covered the two things, downloading the FIRS file and doing the astroplan observation. We could not get time to I should discuss this. So for the next thing I have to do, that is the thing, accessing the SDSS database in Python. So here for that, star formation question 2. So this the original version of this code is taken from this link, and the main key objectives are to explore the scaling relationship among the star forming galaxies. And the first objective for this today's code, running this code, is the accessing the astronomical datasets. So for accessing any astronomical datasets, you have to you can use the Astro Query package, one basic package for querying datasets, and you have some introduction to the standard query language. We will see how it works. So for that you have to just go through this notebook. You will be you have to install the or import the pandas. You have to install the NumPy, the plotting image read imrate, astropy.coordinates c, astropy.units u, astropy.coordinates as coordinates, astropy.coordinates sky coordinate, ASCII fits, those things from astropy you should import. The main thing you have to install for this code is the astroquery.sdss, import sdss, the astroquery.symbol, import symbol. Now I will check if I have to install this astroquery or not. you have to install here. Explain it all. I should put here. Pip install Astroquery. Pip install Astroquery. If any of the packages has been not installed in your working directory or working disk, you have to install that when you are using Colab. So this code run. Now we will make this few lines for making the note a clean appearance of the notebook. Now several SDSS schema or the technical things will be used in this tutorial. We will not discuss that. And the several properties of the galaxies, such as the redshift of the galaxy, that is the where the galaxy how far the galaxy is from us, what is the emission, the flux of different emission lines, that is the flux amount of light emitted at different frequency or wavelength will be used. When such light emitted from the galaxy or the flux emitted from the galaxy is the H alpha emission line or the H alpha flux. This flux is very sensitive for the star formation rate of the galaxies. If it is observed that the galaxies with the high star formation rate have high H alpha flux, and we will, for this quote, this H alpha flux is often, and also the thing is the H alpha flux is the optical flux, and it get absorbed by the amount of dust in the galaxy. So when we plot the luminosity of the galaxy in the H alpha with the H alpha wavelength or frequency, we use two of emission line. We use another emission line flux, that is the H beta line flux, to correct for the dust absorption. The main thing for the running this code is to demonstrate how to get the SQL query with the Astroquery and download the data from SDSS server within few seconds. So for that, suppose I want to create, I want to get some data from the SDSS galaxies which have high H alpha flux. So for that, I am creating that. I have created this query, or we have created this query. So here is this query. If you are familiar with the SQL data structure, you are advised to go to the each lines and get the information, or else I will tell you to just run this code, because it will help you to see within how first we can get the data results with Astroquery. So here is the thing. So you have seen that within 7 seconds we have downloaded data of about 10,000 galaxies from the SDSS database with using Astroquery. Now you can just check galaxy is equals to pd.dataframe ls gals data frame panda had a data frame, and here's pandas data frame star formation. Gals. Now we will use some technical theme from SDSS, and we will correct the H alpha flux that is given in the SDSS database for absorption. you are advised to go this deriding of spectrum steps. I will not go here. And from here we can calculate the luminosity. You can get some H alpha, deridant H alpha flux, that is the corrected H alpha flux for dust corrected H alpha flux. Then from the astropy units, with the unit conversion, you can convert the H alpha flux to H to H alpha flux to H alpha luminosity. So for that you need the flux luminosity relation. You know flux is equals to luminosity by 4 pi dl square, where dl is the luminosity distance, and you can calculate this luminosity distance using the Astropy .cosmology package. So you can just run this code by yourself. We have written the code and just gave you some small essence. So you have to import unit the knowledge of the astropy.cosmology and also astropy.units for this kind of luminosity flux to luminosity conversion. Now you can just get the luminosity, H alpha luminosity values, and for the conversion of the luminosity flux to H alpha luminosity to the star formation rate, there are some typical relations, and here on this relation has been mentioned, and in some part of this tutorial or this tutorial notebook, the link for the paper where this star formation rate to the luminosity to star formation rate has been mentioned. We advise our learners to go through those, and you can plot just the star formation rate from the this luminosity, this H alpha flux given in the SDSS database, and you can plot those at the log form, different kind of log form, log plot, those things you can check by yourself. The next thing we will see, we will not run this code. This codes will be provided to you, and this specific star formation rate d tau d, that is the doubling time time, those things can also be done. The next thing we will do, how to download the SDSS spectra within few seconds. So if you go to SDSS database, you will see that there are different identification for the each spectra, and this each spectra is identified by the plate MJD fiber. The plate is the plate MJD fiber. The MJD is the time when it taken, and the fiber ID and the plates are the two other identifiers. So this plate MJD fiber, this is the key identity of a SDSS spectra. If you know the key identity of some key identity of galaxies in astronomical database, it is you can using their pipeline or their query tools, you can download the information of you can download all the informations of those galaxies within just by few lines. So each galaxy surveys, or each galaxy survey or any survey for exoplanets or solar system objects have identifiers. Your first task is to check what is the main identifier of your data set. Now for the astronomical spectral database of SDSS, there have millions or billions of spectra you can say, and each of the spectra has been identified by by this ID, that's plate MJD fiber. For other astronomical database such as the TASE database for exoplanets, exoplanet research, those also have some key identifier keys. So if you want to work any of the astronomical datasets, we suggest you to go check the identifiers, and check how the database is structured, and if there is some Python based pipeline or Python based querying pipeline thing for accessing those database, and just run the Python codes, and you just get the pandas, the data, whole data, get the pandas data from, and work with it using your own Python. Now you can just check. I will be using this ID plate MJD fiber, plate MJD fiber, and this you have to just SDSS.get spectra plate MJD fiber. Plate number is 1673. I have chosen one galaxies from the list. Fiber ID is 475 and MJD is 53462. So this you can get. I should be able to get the data. So this is the spectra. I should not limit anything. This is the spectra of the starburst galaxy. You can see this is not the continuum subtracted spectra. Here, because there the flux lambda is given, this is about 10 to this is in the unit of, I guess, 10 to the power minus 17 ox per second. You have to check the website for the exact unit. So by this SDSS.get spectra, you can download the spectra of the not continuum unsubtracted spectra from the SDSS data browser. So for the today's class, we discussed how to download the images from the HIPS2 cutout and plot those in this AstroPy. We checked how to get information of some objects to observe from the position, from a particular position. Next, we got introduced how to use the Astro query for your own work or any kind of small projects, and how to plot the SDSS galaxies. So in every astronomical database, there is some key identifier of the object, key identifier of the object's data, key identifier of the observation. And for downloading the data, you have to know, or you have to check where the data is, how to access the data with the ease and with the very you have to find out what is the which step is taking which the less time for you. So this are the thing where the notebooks are taken from different material, or those books are copied from different materials, you can say. This I should specify that this is not on my own notebook, and this has been made by other experts, and I am just discussing those, and these are the links from where I have copied. And the thing, this ends today's lecture, and this ends also the lecture of the course of the Introduction to Astronomy and Astrophysics on ISSS platform. Thank you for joining. If you have any review regarding the course, you can feel free to write to me. And thank you for joining. Thank you.